I am Sarbashis Kumar. Today I am discussing about a series, P series. Let's see. Theorem. The P series, the infinite series 1 by 1 to the power p plus 1 by 2 to the power p plus 1 by 3 to the power p plus 1 by 4 to the power p. In this way 1 by n to the power p plus dot dot dot. This series will be convergence. This series converges if p is greater than 1. This series converges if p is greater than 1. Diverges if p is less than equal to 1. If 1 by 1 to the power p plus 1 by 2 to the power p plus 1 by 3 to the power p plus 1 by 4 to the power p plus dot 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 1 by n to the power p plus dot 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 converges if p greater than 1. Diverges if p less than equal to 1. Converges if p is greater than 1 and diverges if p less than equal to 1. Proof. Case 1. Case 1 means this. Converges if p greater than 1. Now we prove that. Suppose p is greater than 1, then we show summation 1 by n to the power p converges. Suppose p is greater than 1, we show that summation 1 by p converges. First, we examine the partial sum of the order 2 to the power n minus 1. First, we examine the partial sums of order 2 to the power n minus 1. S 2 to the power n minus 1 is equal to, you put here n equal to 1, n equal to 2, so you can write 1 plus 1 by 2 to the power plus 1 by 3 to the power p. But here you keep 2. Here you keep 4. 1 by 4 to the power p, 1 by 5 to the power p, 1 by 6 to the power p, 1 by 7 to the power p. In this way, here you keep 4 term. Here you keep 8 term. In this way, 1 by 8 to the power p, 1 by 9 to the power p, dot dot dot, 1 by 15 to the power p. Okay, and here you put enter. Now here you put, here 8 means 8 term means 2 to the power 3, so here you put 2 to the power n minus 1. Okay, now you see what you see. If you put here instead of 3 2, then division will be here 3, division will be less, and here this is 3 is greater than 2, so here division will be less, here division will be greater, and that's why this is greater than equal. Okay, here 5 to the power p, you keep 4 to the power 7, 4 to the power p, here 8 to the power p, 9 to the power p, you keep 8 to the power p, 15 to the power p, you keep 8 to the power p. In this way, let's see. Again we discuss. At first we write this, and we first term 1 and second term you keep 2 term, third term you keep 4 term, 8 term, in this way, and and then you put 3 by 2, here you put 5 by 4, here you 7 4 by p, and this term 5 is greater than 4, 5 is greater than, that's why the division here less, here division is greater, that's why it is greater than equal to 1. Now 2 into 2 to the power p, 4 into 4 to the power p, 8 into 8 to the 1 by 8 to the power p. In this way 2 to the power n minus 1 into 2 to the power n minus 1 p. So you divide here 2 to the power p minus 1, here 2 to the power p minus 1 square, here 2 to the power p minus 1 cube, here 2 to the power p minus 1 n minus 1. Then this is a geometric series, so you can write 1 minus r to the power n by 1 minus r, summing geometric series. So s 2 to the power n minus 1, 2 to the power n 2 to the power n minus 1 is less than 1 by 2 to the 1 minus 1 by 2 to the power p minus 1. From this you can easily understand. So this is constant. Now for positive integer m, now for any positive integer m, there exists a positive integer 2 to the power n minus 1 which is greater than m. Obviously in this case the sequence of partial sum is monotonic increasing, hence 2 to the power n minus 1. So if 2 to the power n minus 1 is greater than m, then s 2 to the power n minus 1 is greater than sm. Since it is a monotonic increasing, partial sum is a monotonic increasing, and that is the condition of monotonic increasing. So you can write Sm is less than 2 to the power n minus 1 is less than 1 by 1 minus 2 to the power p minus 1, which is constant. So all the partial sum are bounded. Thus the sequence of partial sum being monotonic increasing and bounded must converge. Okay, all the partial sums are bounded, all the partial sums are bounded. Thus the sequence of partial sums monotonic increasing and bounded must converge. It is the theorem of convergence. If the monotone increasing bounded above, so it must converge, and that's why it is converged. Hence the series converges if p greater than 1. And now case 2, suppose p is less than equal to 1. We show that here, write the this is divergence series. We have to show. First let us, you put here 1, so you can write these second term 2, third term therefore in this way you can write. So if you put 1, if you put p equal to 1, since p is less than equal to 1, so this term, the division of this term is greater than less than division of this term, as because if you put p equal to half, then that is equal to 1 by 2 and that is equal to 1 by 4. So this term is greater, this term is less than, so this is greater than equal to this. So you can write this again. If you put 1 by 3 equal to 1 by 4, that is 1 by 3 is division is greater than 1 by 4. That's why this term is greater than this. So the 1 plus half, that is 2 into 1 by 4, that is half, that is 4 into 1 by 8, that is half. So in this way you can write 1 plus n by 2. This way you can write s2 to the power n is greater than 1 plus n by 2. Given any number g, that term is greater than g. Given any number, no matter how large, we have s2 to the power n is greater than g. For n equal to n greater than 2 g minus 1, this is, if you put here g, then you get this. Since this is greater than g, and that's why n is greater than 2 g minus 1. So s to n is greater than n to n greater than 2 g minus 1. Further, the partial sums are strictly monotonic increasing. See, if m is greater than 2 to the power n, then sm is greater than s to the power n. This is monotonic, and greater than g for all m is greater than 2 to the power 2g minus 1. So in order to partial sums are unbounded, if bounded then convergence, that is unbounded. Whatever you put the value of g, this is greater. So unbounded, hence the sequence of partial sums being monotone increasing and unbounded must diverges to infinity. Thus the diverges if p is less than equal to 1, and converge if p is greater than 1. That is my complete proof. Thank you.